Hello everyone, I'm Fan1 from Yongchen University, Shanxi Province, China. It's my great honor to give a talk in this great conference. The topic of my talk is cohesive communities in dynamic brain functional network. The brain is a very complex system. In the research of a brain network, we always define the brain regions at different scales as the nodes, and their direct structural connectivity or functional interactions are regarded as the edges. In brain network, there are a group of densely connected nodes, which are called modulars or communities. Modularity is an important character of brain functional network and provides the source of separation of specialized functions with various cognitive domains. To fit different cognitive states, the functional connectivity of two distinct brain regions could be strong or weak dynamically, leading to reconfiguration of brain modulars. In the modular reorganization process, every node in the network can possibly switch between different modulars temporarily. As shown in this toy figure, node 5, 13 in the first switching event and nodes 5, 13, 15 in the second switching event joined two different modulars during switching events. However, it has been revealed that there are modulars that are essentially indivisible in many realistic networks. But whether this type modular is present in brain networks and what functional rulers are they playing are unclear. To address these questions, we first applied the overlapping sliding time window approach on fMRI data to construct the dynamic brain function network. In this approach, a certain length time series from the first time point is cut out to construct the first brain functional network. The certain length time series is called a window. Then the window slides forward one time point along the time series to construct the second brain functional network, and so on to the last time point. The set of brain functional networks obtained by this approach is deemed to contain brain dynamic functional connectivity information. We then use the greedy algorithm to divide every network into several modulars. Then the change of a node's modular affiliation can also be detected before and after a brain functional network state switching event. Here, we introduce the community solidification degree to detect the cohesive communities. The community solidification degree of one node pair is defined as the proportion of modular reconfiguration events in which the node pair stays in the same modular. In this function, CIP multiply CJP equals 1 if node I and J are in the same community in brain function network P, and the CIP multiply CJP equals 0 otherwise. Observe that the community solidification degree is 1 if node I and J are affiliated to the same community among all of the brain functional network. The figure shows the community solidification degree of all node pairs, and the values shown in yellow color are equal to 1 and mean the node pairs solidified to the same defined modular along brain functional network dynamic evolution. Finally, 3 cohesive communities are revealed. They are located in the anterior, middle, and posterior of the brain, respectively. The other 19 nodes that do not belong to the 3 cohesive communities are picked to constitute the control group. as nodes in the three cohesive communities are special in terms of the modular properties of brain function networks, we wonder whether the three cohesive communities display special rulers in brain function network. To address this question, we first calculate the clustering coefficient and the characteristic path length to clarify the functional segregation and the integration of the three cohesive communities. The results show that the clustering coefficients of the three cohesive communities are higher than the control group, which means strong functional segregation in these cohesive communities. Meanwhile, the characteristic path lengths of the three cohesive communities are lower than that of the control group, which means strong functional integration in these cohesive communities. The sample star stands for the significant difference. The cohesive communities are stable, which means they will not be broken in the dynamic switching of a brain function network. This property may relate to the complexity in information processing of node pairs in cohesive communities. In other words, it is expected that functional connectivities between node pairs in cohesive communities fluctuate so less to bond them into the same modular over time. Here, sample entropy is used to estimate temporal complexity of functional connectivity between node pairs. The results show that sample entropy of node pairs in cohesive communities is smaller than the control group. The lower sample entropy suggests that functional connectivities in cohesive communities are more structurally stable and less random. And compared with the control group, the connectivity in both the functional connectivity and the structural connectivity of cohesive communities demonstrates a significantly modular character. The results of similarity between functional connectivity and the structural connectivity also indicate that the functional connectivities of cohesive communities share more features of the structural connectivity, while the control group differs more from the structured architecture. We also test whether the three cohesive communities will be destroyed when the brain is doing cognitive tasks. We first calculate the community solidification degree of 4 cognitive task brain function networks by applying same research process used in resting state brain functional network. The top panel of this figure shows the community solidification degree of the whole network for the 4 tasks. The bottom panel shows the community solidification degree matrices of the 3 cohesive communities. It is obvious that community solidification degrees are equal to 1 within the 3 cohesive communities, suggesting the brain reconfiguration and the task stimulus have little influence to the modular structure of cohesive communities. So, the main conclusions are that, first, the brain functional networks have several cohesive communities in resting state dynamic reconfiguration. Second, the cohesive communities have higher clustering coefficients and lower characteristic path lengths, indicating cohesive communities are the parts of a brain network with higher information processing efficiency. Third, the cohesive communities show more similarity between functional connectivity and the structural connectivity compared with other brain regions. Finally, the cohesive communities existing in resting state are also present in task state, indicating the cohesive communities are robust to external stimulus. That's all. Thank you.